Welcome to the first video on the wonderful topic of quantum mechanics. Now this image here doesn't really have anything directly to do with quantum mechanics, but there's light and whatnot and other things that can be explained with quantum mechanics. So here we go. The story of quantum mechanics typically starts with a guy named Max Planck, or sometimes pronounced Planck, here in America, I guess. Quantum mechanics, as opposed to some other areas of science, was really developed over a number of years by a number of scientists. That's true to some extent for all scientific advancements, but particularly true of quantum mechanics. But we always tend to start with Planck, so let's get into it. First, we have to talk about a little thing known as black body radiation. Kind of a strange name, but this is the idea that an object can emit radiation for a number of reasons. It can be reflecting radiation, so like a mirror reflects radiation pretty well. It can be giving off radiation due to some chemical reactions, and that gives different colors to fireworks and things like that. But if the only reason that an object is giving off radiation is because of its internal heat, we call that thermal radiation. And if we have an object where most all of the radiation that's coming off of it is thermal radiation, we call that a black body. So typically we think of hot objects like glowing metal or molten lava. Those things tend to not be reflecting a whole lot of radiation. There's not a lot of chemical reactions going on. They're just glowing because they're hot. Now colder things also give off thermal radiation. It just tends to not be in the visible spectrum. So this is why we use hot things as an example. But this keyhole thing here is another interesting thought for a black body. So in this case, if we consider the cavity on the other side of the door, imagine a closet or something, any light that goes in this keyhole into the closet is not likely to bounce around and reflect back out the keyhole. So any radiation that is coming out of this keyhole, and there will be some thermal radiation coming out of the keyhole, is due to thermal radiation, as I just called it, not due to reflected radiation or something like that. So that's the idea with a black body. The reason we have that definition is because if we look at objects that are just emitting thermal radiation, they have some interesting properties. We get these nice curves here that tell us the relative intensities, so the relative brightness of a whole bunch of frequencies. We've got frequency on the top here. That's actually increasing to the left, but because the wavelength is inversely proportional to the frequency, that increases to the right. You can have graphs going either way, it doesn't really matter. But the point is, you get all kinds of frequencies or wavelengths of light in different proportions, and so you get a peak proportion here and then lesser amounts here. And these peaks move a little bit, depending, not a little bit, quite a bit, depending on the temperature. So at 3000 Kelvin, your peak radiation is going to be in the red part of the visible spectrum. At 4500, you're going to have your peak in the orange. At 6000 kelvins, you're going to have your peak radiation in the green. Now that's not saying all the radiation is green. It's just saying this radiation right here is green, this radiation right here is orange, and this radiation right here is red. You still get radiation of all parts of the spectrum coming out from a black body. It turns out that the frequency, the peak frequency, so we'll use a subscript P, is proportional to the temperature. And since the wavelength is inversely proportional to the frequency, we get this relationship here called Wien's law that says the wavelength, the peak wavelength, is inversely proportional to the temperature. And just fitting some data to the peaks on these curves, we find this coefficient here. These are not quantities here, these are just units, so meters times kelvins. So you need to plug in a temperature in kelvins, and it will give you a wavelength out in meters. Now you might think, I've seen some objects that glow red or maybe orangish, but I haven't really seen an object that glows green. So let's look at that. So these are the same black body curves here, but here I can adjust the temperature. Those other curves were kind of static. So here, if we lower the temperature a bit, down to the temperature of a light bulb, well, a light bulb doesn't necessarily glow red because it peaks outside of the visible spectrum, and then you get kind of this visible light here. Now if we turn up the temperature, if you've ever stuck a piece of metal in a fire, maybe you were roasting marshmallows with a coat hanger and you left that in there, you notice that at first it starts to glow red because that's the lowest temperature where you get a peak in the visible spectrum is going to give you a red peak. Now as it gets hotter and hotter, right here it shows kind of the composite color that you're getting from an object at this temperature. So as it gets hotter, here we get to the green peak I was talking about. I've got to zoom out here. When it peaks in green, you get a whole lot of the other stuff too, which is why the green doesn't necessarily stand out so much. That's when it starts glowing kind of white hot. And then as the temperature continues to rise, then it could actually start glowing blue. And here you have quite a bit more blue than the other colors, so the blue is able to drown this out. And we see this with stars as well. The coolest stars are red, and then you get kind of yellowish, whitish stars, and then the hottest stars are blue. All right, jumping back to our PowerPoint. So we had this nice equation that predicted the peaks of these curves for a specific temperature, but the issue was we couldn't predict the entire shape of the curve, just the peak, even though we tried hard to do so, until Planck did it, and he gave us this wonderful, beautiful equation here. Don't worry, you don't need to write this down. We're not going to use this. This applies to the red curve, and this was the actual curve that they measured from experiment from the data. So this was the correct curve. Now, Wien, who gave us Wien's law, his curve was the green one here, and it matched pretty well. It matched actually really well at low wavelengths or high frequencies, but it got off by a fair amount here. So the green one was the Wien, okay? And then we had some other contenders. This one is known as the Rayleigh-Jeans law, and you don't need to know all of this necessarily, but you know, it's always good to be educated. Jeans, okay, so this was the Rayleigh-Jeans law. A couple of people worked on that one. And that one matched terribly at high frequencies or low wavelengths, but if we extrapolated this further to the right, you'd see that it actually matches better than Wien's law at large wavelengths. So this one worked real well way over there, and Wien's law worked well over here, but neither of them worked well for the entire portion of the spectrum until we had Planck's law. By the way, this thing shooting up goes going crazy up here. That was known as the ultraviolet catastrophe. Wonderful name here. Catastrophe, or sometimes known as the Rayleigh-Jeans catastrophe. So Planck did this. Hooray, way to go, Planck. But this was just kind of one piece of data that needed to be fit, and that really wasn't the important thing. The important thing was some of the assumptions that he made in order to get this big, beautiful expression. Particularly, he had to assume, and the others doing this curve fitting didn't make this assumption at all. They had more normal assumptions about how energy worked. So he made an assumption that has come to be known as the quantization of energy. So to quantize something means to break it up into its smallest chunks. So a little bit of background. We knew that in order to produce electromagnetic radiation, you had to have moving or accelerating charges. So we figured that this thermal radiation was due to the charges in the material itself jiggling back and forth, oscillating. And that's what was producing this energy. And then we decided that, well, Planck decided that we could only have an integral multiple. An integral multiple means you have to multiply by an integer of some constant times the frequency of the oscillation. Okay, so now we say that energy is quantized for a specific frequency. Okay, so for a specific frequency you can have different amounts of energy, but you can't have any amount. They have to be step sizes equal to integral multiples. Okay, now you can still have any frequency you want, which gives you any energy you want. It's just for a specific frequency you have these specific step sizes, and we'll talk about that. Speaking of step sizes, here's a picture of a step. So the idea of quantized versus continuous, this would be a continuous slope. If you're imagining the gravitational energy, mgy, you can have any value for this ramp. Whereas here, if you've got mgy, you can only have certain y values where we're assuming equal step sizes here. You can't have one in between. The box can't rest here. It would just fall right down, right? Okay, so this is what we mean by quantized. By the way, he found the value for h, this other coefficient in his equation, just by fitting to these same curves. He fit his equation found what mathematical value for that coefficient would make it fit the data, which is something we do a lot. All right, and he found this is the value, 6.626 times 10 to the negative 34th, which is now considered one of the most fundamental constants in all of science. It later came to be known as Planck's constant. He didn't name it that, but others named it that in his honor. These are just units here, joules times seconds. Now, Planck didn't really realize the full implications of his expression here that he used to derive Planck's law to fit the black-body curves. He viewed this more as kind of a mathematical trick, but he didn't really trust the underlying implications on the physics. That took another gentleman by the name of Albert Einstein, and he said that equation tells us that energy comes in discrete packets or chunks, and that is amazing. That is completely contrary to what we now call classical physics. That idea never showed its face anywhere. And he also realized that we have these oscillations giving off electromagnetic waves, and they give off energy in certain packets. And so if I want to know the energy of a single packet, I just get rid of that n. And basically I set n equal to 1. So I want to know a single one of those packets. And this here is the energy of a single packet of electromagnetic energy, and he called those packets photons. We can also substitute in, because the velocity of any wave is equal to its frequency times its wavelength. So frequency is velocity over wavelength, and the velocity of an electromagnetic wave is c. Did I do that wrong? No, that's okay. Okay, so we plug that in and we get hc over lambda is just another expression for the energy of a single photon. And this is where things kind of got started. All right. More on that story later, but here we'll do a couple of examples of the types of calculations we'll do. For your homework, you will have some Wien's law examples. So if we know the peak wavelength, no, we don't know it, we want to find the peak wavelength of a 20 Celsius object. Doesn't matter what the object is or what it's made of, as long as we treat it like a black body. None of that matters with thermal radiation. So Wien's law was peak wavelength equals 2.9 times 10 to the negative third meters Kelvin over temperature. I'm going to go ahead and plug in the temperature here. So 20 degrees Celsius, we need to add 273 to turn that to kelvins. And so then our kelvins cancel, and we end up with 9.898 times 10 to the negative sixth meters. Now, often we like to write our wavelengths in nanometers because people just tend to remember better. The visible spectrum, need an E in there, is 400 to 700 nanometers. So then we can kind of compare where in the spectrum we're located. This works out to be 9,898 nanometers. So this works out to be in the infrared part of the spectrum. So the wavelength is too big for the visible spectrum, and bigger wavelength means lower frequency, lower energy, and that's infrared. You might think that's quite a bit outside the visible spectrum, but we don't get microwaves until like 1,000,000 nanometers. They tend to be like a millimeter wavelength. So that would be a microwave. So this is well within the infrared part of the spectrum. All right, one more example. So if we're given the energy of a photon is 3.2 electron volts, if you remember these electron volt units, we used those back when we studied particle physics. That can break the bonds of your DNA, so these are the ones we need to worry about if we are going to the beach. And we want to find the wavelength of these photons, because if we know the wavelength, we can protect ourselves from those wavelengths, right? So we're going to use, there was a couple of expressions relating energy to frequency and wavelength. The wavelength version was hc over lambda. Now we're going to solve for lambda, so we just rearrange a little bit. Hc over the energy. Okay, now with Planck's constant, I'll go back and forth between Planck and Planck. Pretty sure the Germans pronounce it Planck, but anyway, earlier I showed you it was 6.626. Often we're just going to round it to 6.63 because why not? Times 10 to the negative 34th. And then we've got c, which is the speed of light. To 2 decimal places, it's actually 3.00, so you guys can just plug in 3 in your calculators and call it good. Now the energy here, since Planck's constant was joules times seconds, this is meters per second, so seconds are going to cancel. We're going to have joules up here and meters here. We want a wavelength, which is meters, so that means our energy on the denominator needs to be in joules, and we're giving it in electron volts. So 3.2 electron volts. So we're going to have to multiply by a conversion factor, and it's been a while since we've used this, so you probably need to write it down. It's 1.6 times 10 to the negative 19th joules per electron volt. So the electron volts go away, the joules go away, and we just get a nice answer in meters. This one comes out to be 3.88 times 10 to the negative 7th meters, which we round gives us about 390 nanometers, which was just out of the visible spectrum on the other side of our previous problem. So this is an ultraviolet photon here. Those are the ones that we need to worry about. All right, see you next time.